You know how some technologies feel like pure science fiction, right? Just stuck in a book somewhere. Until, all of a sudden, they're not. One day, it's just a wild idea, and the next, it's actually starting to change our world. Well, we're at one of those moments right now, at the very beginning of what everyone's calling the quantum decade. So let's dig into what that really means.
So here's the deal. The engine that has been powering our entire digital world for more than 50 years, well, it's hitting a wall. A fundamental wall. That predictable exponential growth in computer power that we've all just taken for granted, the very thing that makes progress happen, it's slowing down. And with that engine basically running out of steam, it brings up the biggest question in tech today. What comes next? I mean, where do we possibly go from here? To really get a handle on what's coming, we first need to understand the limits of what we've got right now. Because this isn't just about a simple upgrade. This is about starting a completely new chapter in the whole story of computing. See, way back in 1965, this brilliant guy named Gordon Moore made an observation that pretty much became a self-fulfilling prophecy. This law has been the relentless heartbeat of progress, making our phones, our computers, our entire digital world faster, smaller, and cheaper, year after year after year. It's the foundation our modern world was built on. But we're facing some major headwinds now. We have shrunk transistors so small that we're literally measuring their parts in a handful of atoms. The effort and the money it takes to keep this up has become absolutely astronomical. The bottom line is, we're bumping right up against the laws of physics. You just can't shrink silicon any further. So, if the answer isn't just making our current computers better, what is it? Well, the answer is to build a totally new kind of computer, one that plays by the bizarre and frankly wonderful rules of quantum mechanics. To get the difference, you gotta start with a basic building block. Every computer you've ever used is built on bits. They're just simple switches, either on or off. A 1 or a 0. That's it. But a quantum computer uses a qubit. And a qubit, this is where things get really weird, can be a 1, a 0, or, incredibly, both at the exact same time. Yeah, this ability to be in many states at once is called superposition. The best way to picture it is like a spinning coin. While it's spinning, it's not heads and it's not tails. It's in a state of both possibilities at once. This is what lets a quantum computer explore a huge number of potential answers all at the same time. And if you thought that was weird, get ready for entanglement. This is where two qubits become deeply connected. Whatever happens to one of them instantly, and I mean instantly, influences the other one, even if they're on opposite sides of the universe. It's a concept so strange that even Albert Einstein was totally baffled by it. He famously called it spooky action at a distance. And that tells you just how much power we're starting to tap into here. Now, a lot of people think this means your next laptop is going to be a quantum computer. But nope, that's not the goal at all. Instead, think of them as highly specialized partners designed to work right alongside our regular computers to solve very specific, very hard problems. And hey, this isn't just theory anymore. This is what a real quantum processor looks like. What you're seeing here with IBM's Eagle processor. Those incredibly intricate layers, those are the superconducting circuits that become the qubits we've been talking about, the parts that actually harness all those strange quantum effects. So how does this partnership actually work? Okay, imagine a super complex supply chain problem. A normal computer handles all the basic data and the workflow. But for that one ridiculously hard optimization part, the piece with millions of variables, it just offloads that to the quantum computer. The quantum processor does the insane heavy lifting, finds the best possible answer, and then sends it right back. They're a hybrid team. So why does any of this matter? Because this partnership is going to let us take on problems that right now are completely impossible. And I don't just mean hard. I mean problems that would forever be impossible for even the world's biggest supercomputers to solve. So in healthcare, for example, it means we could finally simulate complex molecules with perfect accuracy. That could let us design personalized medicines, things that are tailored exactly to your biology, and move way beyond one-size-fits-all treatments. In energy and climate, it could help us discover brand new materials for crazy efficient batteries or solar cells. We could figure out how to perfectly optimize our energy grids for renewables. I mean, that's a massive step in fighting climate change. And yeah, for the devices we use every day, it means designing new materials right from the atomic level. Creating things like brighter, super power-efficient screens for our phones that would make batteries lost for days, not hours. To really get this scale of this jump, just look at this number. To accurately simulate a single kind of complex molecule on a classical computer, you'd need 10 to the power of 106 bits. That number, it is vastly bigger than the estimated number of atoms in the entire observable universe. It is, by definition, impossible. And now look at this number. Using a quantum computer, you would need just 354 stable qubits to represent that exact same molecule. We go from impossible to 354. That is the monumental leap in power we are talking about. So where are we on this journey? We are right at the very, very beginning. It's like we're standing at the shore, and we can feel that tide start to pull out just before a massive wave comes rolling in. Researchers see this whole thing rolling out in about 3 ways. Right now, we are in low tide. These are the early days, the lab experiments. Soon, we'll get to high tide, where breakthroughs start to happen more often. And then, finally, the tsunami. That's when we achieve quantum advantage. And this technology really starts to reshape whole industries. We are living in the quantum decade, and it leaves us with the most exciting question you can possibly imagine. With a tool that can finally solve the unsolvable, what impossible problem will we choose to solve first?